Hello and welcome back to Automata, Grammars, and Computability. Now, in this video, we're going to talk about Turing machines a little bit more. One thing I haven't really told you about yet is the halting problem. The halting problem is the question of, can a Turing machine decide whether another Turing machine will halt on a particular input? So the idea here is I have a Turing machine that's literally going to take another Turing machine as its input. Which you can do because it turns out everything can be represented as a string. Now, just remember, not halting means we go into an infinite loop, and that causes a limitation in what Turing machines can compute or decide. So we mentioned that Turing machines could accept, reject, but they could also just loop forever. Now, with that, maybe if we add some more features, we could get a more powerful machine. So today we will talk about some Turing machine variants. Let's think about new capabilities that we could add to a Turing machine. And by capabilities, I mean things other than magic, oracles, or time travel. And please do read section 3.2 in CIPSR to get a better sense of what's going on here. So I didn't give you magic, I didn't give you oracles, I didn't give you time travel. What could we add? Multiple tapes is one option. Non-determinism is another option. And just remember, when we talked about DFAs and NFAs, adding non-determinism didn't add any power to the finite state machines. But with pushdown automata, having non-deterministic pushdown automata, those were more powerful than a deterministic pushdown automata. And I do recommend just pausing the video and thinking about other things that you might like to add here, other possibilities. Of course, you want to add magic, oracles, and time manipulation. Those things are things that you can do, actually. We do have the concept of oracles, and with time machine, it's time manipulation. Sometimes we deal with that if we're dealing with quantum Turing machines, which is a thing. And with quantum powers, you do have like the possibility of quantum entanglement and other things like that. So sometimes that's going to be something that you use, but anyway, not for today. If you're interested in learning more, of course, do read the chapter, which talks about multi-tape and non-deterministic. So that's for CIPSR, but there is a more exhaustive list on Wikipedia. One example of something you could add is a single tape, multi-tape. Okay, so CIPSR's got that, but what about a two-dimensional grid tape where you can go north, south, east, or west on the tape? And that one's interesting, so I'm tempted to make an exam question about it. Another possibility is the oblivious Turing machine, where the tape head is independent of the arrows. You could have counters for unbounded registers. You could have random access stored programs, which is a von Neumann architecture, but please do read Wikipedia if you want to know more. And you can go to Wikipedia and read more, like I just mentioned, or just sit down and think about other possibilities that you might like to try here. So let's talk about the multi-tape Turing machine. So as before, as we've always had since DFAs, is we have finite control. And the finite control also has the tape associated with it. And now I have n tapes. So like n tape symbols to match, one for each tape, n tape symbols to write, one for each tape, and n directions to move, one for each tape. So for example, let's say that we were going to move from state Q4 to Q5. I can add three sort of things here: S6, Q4, R2, which would be this kind of this first tape right here, S6, being in state, looking at element S6, and then that tells me where to move. And S6, Q4, R9. And so I can do stay, and write with each of these. So it's kind of like having an array of tape symbols. So just S6, Q4, and R2, and then I have S6, Q4, and R9, which is not even drawn on here. Turing does have this as a definition, and it's formalized. So I recommend making formal definitions because it helps you understand specifically what it is you're looking for. And the thing that has changed here is I now have gamma to the k. With k tapes, I can have gamma to the k tape symbols. It's like having a k-length array. The other thing that I have here is LRS to the K. So S here means stay, whereas previously we've used N, but I have K possibilities of where to move, one for each tape. Now, the real question for us is I did all this stuff, I gave you all these tapes. Does it give you more power? Do you have now the power to solve problems that a single tape Turing machine cannot solve? And it turns out it doesn't. So just like with when we did DFAs and went to NFAs, I didn't get any additional power. The thing that helps, though, is with more tapes, I can get a polynomial increase in speed. So speed is measured by counting the number of state transitions, and it might be possible to solve the problem faster by having additional tapes. But in the end, if I don't care about like speed or efficiency, in terms of like the truthiness of it all, the set of languages accepted by multi-tape Turing machines is exactly the same set accepted by single-tape ones. And now the question is, well, how do you prove this? If you go to Sipser, Theorem 313, it has a proof by construction. It shows how to convert a single tape machine that simulates having 3 tapes. And what you can kind of see here is I had 3 tapes with M, and then I just use this hashtag to split out different sections to indicate new parts of the tape. And now I'm doing with 1 tape what I did with 3 tapes. Another thing I'd like to point out in terms of like what the book is doing, there are marked symbols on top of the cell. It's like a circle, and that indicates where the tape head is on the multi-tape Turing machine that we are simulating. So here, the tape head was at 1, and the third A and the first B. And so with the bottom here, that tape head with that circle is at 1, and the tape head with the A, third A has the circle, and then the tape head with the B has the circle. Another approach to prove this is to enlarge the alphabet so that each symbol is a triple, which I kind of like, meaning that X is on tape 1, Y is on tape 2, and Z is on tape 3. So I would just triple the alphabet. And as before, I have marked symbols to indicate where the tape head is on the multi-tape machine we are simulating. So one question I have for you to think about is how many symbols are needed to do this 1 tape Turing machine. And then another question that I have for you to think about is how does this 1 tape Turing machine actually move along the tape? If I can only move left and right, how do I know how to move for the finite state control? So now the question that you might have here is, well, I didn't add any power, so why on earth would I bother with using a multi-tape Turing machine, which is a little complicated anyway, with figuring out where to move. It is sometimes more convenient because you could use 1 tape for the input and then use other tapes for scratch work. And please do go to TuringMachineSimulator.com, check out fast binary palindrome, and see how doing fast binary palindrome 2 tapes is faster. In some cases, it can also simplify some proofs about Turing machines. So why, again, continuing, why use the multi-tape Turing machine? Fast binary palindrome uses 2 tapes. But why is it described as fast? Fast for us is just going to mean using fewer steps that are needed to reach accept or reject, assuming that the problem halts in the first place. Because a single arrow label is an action now for k tapes. So you're basically like looking at k things at once. And so that means that speed up of the Turing machine is polynomial in the number of tapes. To see the proof for this, more specifically, you should read Hartmanis and Stearns, 1965. Go to the AMS and read about this. Or, you can just follow any references in CIPSR to learn more. Okay, another thing that we could maybe add to Turing machines that makes sense based on the stuff that we've talked about before is adding non-determinism. So here, how would non-determinism look in a Turing machine? Well, in that case, we would have more than one arrow out of a state for a given tape symbol. You could have epsilon arrows. So this should all seem familiar if you got comfortable with what was happening with NFAs and also with pushdown automata. A non-deterministic Turing machine then kind of like pretends like every arrow out of a state is followed in parallel or simultaneously. So with non-determinism, you consider all paths through a deterministic Turing machine, and how do you know if that Turing machine accepts or rejects? So non-determinism kind of implies that a choice can be made. Which arrow do you take? That computation forms a tree of possible computations. The tree branches when there is more than one alternative. That is in comparison to a deterministic Turing machine, which has a linear computation, a sequence of states. So it's kind of like before I just had a path, a sequence, and now I have a whole tree. And as you might have figured out, because we talked about this before with NFAs, if any of those tree branches are going to reach an accept or reject state, then the Turing machine halts. So let's see this tree of computations. We know that it looks like what we had with NFAs. Okay, so here's an example of something with regex notation, and here is an automata that represents it. You can follow along these arrows and see that there are these epsilon arrows because I have that question mark there. And you can see the input AAA. And I'm not going to draw out the whole tree, but I am going to say, okay, from Q1, from reading an A, I could go to Q2, and then do other stuff. And then from Q2, I could go to Q3 or Q4, just kind of depends. But that tree eventually will end in something that looks like it would accept. Pushdown automata, which are also non-deterministic, and non-deterministic Turing machines, which we were just talking about, have these trees of computation, just like an NFA does. So those three things, you should remember them as having trees, and that non-determinism is what gives you that tree. And then if any branch ends in accept or reject for a Turing machine, that's the thing that's a little bit different. That means that Turing machine halts. Okay, though, it didn't give us any more powers. Non-deterministic Turing machines and deterministic Turing machines are the same in terms of the language they can find. The proof that any non-deterministic Turing machine has an equivalent deterministic one is a proof by construction using that Turing machine with 3 tapes. You can go to CIPSR figure 317 to find that out. And basically, it constructs a deterministic Turing machine that tries every path through a non-deterministic Turing machine. The Turing machine that is used is a 3-tape one, and we already know that's equivalent to a 1-tape one. Okay, so just to say it again, a non-deterministic Turing machine is equivalent to a deterministic one it goes via proof to a Turing machine with 3 tapes. It's almost like a little of what I'd call a hybrid argument. Turing machine to 3 tapes, and then I know 3 tapes can go to 1 tape. A couple of steps there. Well, are non-deterministic Turing machines even useful then? Like, why do I care? Like, I didn't care if I got speed up, at least not before. And that's all I'm really getting here as well. The other things that might be helpful is it might be easier to design a Turing machine using non-determinism, just like it's often easier to draw an NFA than a DFA. So kind of just up to you, right? Like, do I like an NFA in this problem, or do I like a DFA in this problem? Do I like a deterministic Turing machine in this problem, or do I like a non-deterministic Turing machine? It also depends on what I ask you. So again, I want to make the contrast for non-deterministic Turing machines to push-down automata. The push-down automata for W and then W reverse, which is palindrome, even palindromes, you could not do that with a deterministic push-down automata, but you could do it with a deterministic Turing machine. Here, it was required that you took these epsilon steps because you kind of had to guess when you were in the middle of the string and start popping the symbols off to see if it matched. So do take a look, like take a careful look at this push-down automata that here can either like read the elements or just straight up take an epsilon transition to decide, hey, we got halfway through the string and we're going to keep going, and start looking at the second half. A deterministic push-down automata cannot recognize this language. The other thing, like if you care about speeding things up, which sometimes we do, a deterministic Turing machine can simulate a non-deterministic Turing machine. It tries each possible computation in the tree of possibilities, but the number of steps that you need to do this might be large. And then you could count and say, how many steps does this non-deterministic Turing machine take before it halts, before it does halt? It just halts if there is a path, so it's going to be the shortest path in the tree, right? So a deterministic Turing machine only has one path, which means it's the length of that whole thing. And if you think about it, it's kind of like flattening the tree out. But this non-deterministic Turing machine, you just take the shortest path, you're good to go. The next question is, well, I actually want to program things. Like, can I write a real non-deterministic Turing machine? We could say, okay, I said you didn't have magic, but maybe we could guess correctly for every choice. It could try all choices simultaneously. Yeah, there's no magic. There's no oracles. So that's not going to work. Sorry. The second approach is basically what parallel computation is. So those of you that are interested in vectorization, SIMD programming, these are all ways to get speed up. And I guess sometimes parallelization is good. Sometimes it causes things to give us more pain than it would have otherwise. So you are the designer, you are the programmer, make some decisions. The amount of parallel computation that you're going to need depends on the size of the problem and on the design of the Turing machine. Like maybe you don't want too much branching. And here, I guess I do want to talk a little bit more about this and relate it to some things that are going on in like reality. I mentioned vectorization, which is really important for computation nowadays to get good speed ups. Like that is a real thing people work on. It also can cause problems with trying to sync up all of the computations sometimes. So those of you that are interested in security, this is just a like very quick aside. There has been some like magic in trying to guess which paths are going to be taken. And there were things like Spectre and Heartbleed that were doing this sort of like I'm not going to talk about it more than that, but they were doing this sort of guessing, which caused like all sorts of security issues. And if you're interested, you should look up a little bit about it. So basically that's, I think you have like the whole sense of like, here are these Turing machine variants. They don't give us any more like help in terms of languages that we can recognize, but they might make our computation more efficient. They might make it easier to solve a problem. So that's, for now, that's all I have. And then next time, what I'd like to talk about is talking about the halting problem in earnest, because I haven't really yet. And then finally, we'll be able to start talking about those complexity classes P and NP, where knowing about the difference between deterministic and non-deterministic Turing machines is really important. So that's all I got for you. Thank you for watching.